So, hello everyone, welcome to the seminar today. Today we have a guest speaker, Rhys Seeburger from MPIA in Heidelberg, where he's working with Hans-Walter Rix and Karim El-Badri. He's currently a final year PhD student, and he's going to talk a little bit about black hole impostors. Before that, actually, he did a master's in astrophysics at the University of Heidelberg on lensing cosmology. So this is going to be a drastic shift in the science, but Rhys, enjoy.
Thank you. I think I've unmuted it. Right, fantastic. Thank you, Dr. Janssens, for that very nice intro. If any of you were at your defense yesterday, you'll have seen some of the content of this in sort of broad strokes. So apologies to you. The intro might be a little bit repetitive, but for those that weren't, and even those that were, we'll do a little refresher. But before I dive into it, that title is very long. It describes pretty well what I'm actually talking about. But I've also provided an alternative title for those of you that like to be able to make conversation about it more quickly. I'll be talking about black hole impostors. If you want to play a little game, count how many times I use that little guy in this presentation. But before we can start thinking about stellar mass black holes, it's probably, about black hole impostors, it's probably a good idea to think about stellar mass black holes. So what is actually being imposted here, and what do we think that we know about these systems? And to understand more about stellar mass black holes, we have to understand where they come from. So a quick refresher of anybody's sort of bachelor level stellar evolution course. We try to separate stars into roughly higher mass stars and lower mass stars. Lower mass stars include, for example, the sun. Lower mass stars on the main sequence, they sort of do their thing. They chill fairly slowly compared to higher mass stars. Once they run out of fuel, they become a red giant. That red giant then starts shedding its outer layers, and those outer layers become a planetary nebula, nothing to do with planets, just a naming convention. And the hot core remains as a white dwarf. It's just inert, very hot, and it sort of cools down over a long period of time. Comparatively boring. Much more exciting are high mass stars. High mass stars live fast and die young. They have a much shorter main sequence lifetime, and once they run out of fuel, become a red supergiant, and once stuff happens, which is actually not as well understood as we would like it to be, that red supergiant can go supernova. And then depending on the actual sort of main sequence mass of that high mass star, we get a different stellar remnant, a different compact object, and we call them compact objects because they're very dense. For sort of a roughly 8 to 25, maybe 30 solar mass main sequence star, we end up with a neutron star remnant, and a neutron star is roughly between 1.4 and 2.4-ish solar masses. And for a very high mass star, so a star that was more than around 30 solar masses on the main sequence, we get a black hole. And that's a stellar mass black hole, which is a couple of solar masses, usually, more or less. So above 5, we think, but it might be more or less depending on the actual mass of the progenitor. What's also important, when we talk about high mass stars, most of them are born in binaries. So they're a system of 2 stars that are going around each other, and that's important because those binaries lead to interactions over the lifetime of the star. So this is from San et al. For O stars, so the most massive and biggest stars that we sort of consider. And we know that about 2/3 of them, slightly more, interact with their companion in some way or another during their lifetime. And so there's various ways this can happen. There's envelope stripping, accretion, spin-up, common envelope evolution, there's stellar mergers, but only about 1/3 of them are effectively single. So that includes stars that are actually single, so they're not born in binaries, but also stars that are in binaries, but they're too far apart, so they'll never actually interact throughout their lifetime. So stellar interaction, binary interaction, is incredibly important when we're talking about high mass stars, and therefore it's also very important when we're talking about stellar mass black holes. And going on from that, it's not just important for these O stars, where I've showed this very extreme example. Basically, all of them are binary in some way or another. But this is a plot from Mo and Di Stefano, where on the x-axis we have the mass of our primary, so of our sort of main star in our binary, our heavier star in our binary. And on the y-axis, we have the fraction of stars that are in various configurations. And is there a way to turn off that light, maybe? Or, nope. Yes. I'll just keep going, just because the colors are a little bit hard to see. But basically, here we have the single star fraction, the binary star fraction, the triple star fraction, and the quadruple star fraction. And what we're observing is that essentially for a solar mass star, so somewhere around here, the vast majority of stars are single. But the further you go up in mass, the more and more stars are in some kind of multiple configuration. And around like 3-4 solar masses is where so if we get a turnover point. So actually more of those stars that are a couple of times the mass of the sun are in multiple systems. So just to drive home the point, this is the sort of binaries are not just important in O stars, in the most massive, biggest stars that we talk about, but also B stars, A stars, etc. And these binaries lead to very interesting sort of interactions throughout their lifetime. And the reason that we care about this is because they make interesting products, such as binary black holes. There's a number of possible formation channels, and there's variations of this graph, many, many variations of this graph that you might have seen. But basically, I won't go into detail on this because I'm not a theorist and I don't actually understand all of these steps very well. But basically, the point here is that these objects interact in various ways throughout their lifetime. And there's various sort of formation channels that we can take towards binary black holes. And we care about binary black holes because they do very cool things, like merge. And when they merge, we get gravitational waves. And gravitational waves are super exciting, Nobel Prize, all of that stuff. So we're very interested in understanding where do these systems come from, how do they form, what are their progenitor systems, et cetera, et cetera. And those are questions that we can ask and that we can try and answer if we're looking at sort of the intermediate stages in this graph. So we understand a fair bit about this stage here, binary stars. We're starting to understand more about this stage here, sort of two black holes merging. But what is more of a mystery is all of these intermediate stages, so what's going on in between there. And then this talk here, I'm particularly sort of more focused on the first half, because that's a little bit clearer, a little bit more like slightly more cut and dry. The second half becomes really confusing. There's lots of possible branches. There's only 2 on this graph, but there's more. And in particular, I want to focus on these systems here. So this is what we call a quiescent or a dormant black hole. So we have a star and a black hole that are in a system with each other. And this is what happens when one of the stars has gone nova and become a black hole. So this is something that I very much care about. There's sort of a specific subtype of this class, which is in what we call an X-ray binary. And this is when the star and the black hole are quite close together. So the very strong gravitational attraction from the black hole starts sort of tearing off the outer layers from our star. And those outer layers then get accreted onto the black hole. They heat up into an accretion disk, and that accretion disk radiates in the X-ray. And that's very cool, because very few sources, stellar sources, radiate this strongly in the X-ray and not really in other wavelengths. So this is a very good way to identify these particular systems. What's interesting, however, is that we actually expect only a very small fraction of all stellar mass black holes in the Milky Way galaxy to be in these kinds of systems. We expect the vast majority of them to be isolated. They form in binary, but all in binaries, but once we have a supernova, there's very likely a birth kick. We don't understand the exact physics of this, so the exact fractions are sort of, that's why there's no numbers on this either. This is sort of more an illustrative graph. But basically, the supernova birth kick is going to very likely break apart the binary. But there's also systems where this doesn't happen. So these detached systems, the quiescent or dormant black holes that I've talked about. And only a very, very small fraction of them is going to be radiating in the X-ray, because they need to be quite close for that to be happening. And the phase where they're sort of further apart is much longer lived. And an even smaller fraction of them is going to be merging binary black holes. So this is sort of the expected underlying populations. But if we look into it sort of more with what we've actually found so far, we paint a very different picture. We've found a lot of merging binary black holes, thanks to gravitational waves. We found a good number of these X-ray binaries, sort of in the tens. We found a small handful of detached black holes within the Milky Way and also in the sort of satellites. And we found one singular isolated black hole using macrolensing. So there's something going on here that we probably don't understand the underlying population as well, or maybe much more, also very likely, our observational methods, our finding methods are very sort of biased in one way or another, just because gravitational waves are easier to detect than a singular black hole that's floating around in space and might happen to cause a microlensing event. But what's also interesting is that we actually expect a lot of these binary, so sort of black hole luminous companions, so binary, so black hole and star systems in the Milky Way. So there's a couple of population studies, and this is a graph that a colleague of mine made, just to sort of visualize what we're actually dealing with here. Based on these sort of population studies that people have come up with, we expect somewhere between 10 to the 3 to up to like 10 to the 7 stellar mass black holes in the Milky Way. And this is huge error bars, I know, but we've definitely not found 10 to the 3. We've not even found 10 to the 1, right? So we're like very much at the sort of at the here in the graph in terms of what we've actually found. And that's interesting, because does that mean that we're just really bad at finding them? Does that mean that maybe stellar evolution works differently than we think it does? Does that mean that more of them are isolated, or few of them are isolated, or there's something going on that we don't understand? So it's important to sort of keep the, try and figure out where this discrepancy is coming from. And in order to understand how other systems can impostor or can pretend to be a black hole, we want to look into how we actually go about finding black holes. And one of the main ways that we do that is via a method called astrometry. So if you have worked with Gaia before, Gaia is an astrometry satellite mostly. And what we're looking at here is a binary. And in this example, we've got two components, two bright components, two stars of different masses that are going around each other, and we're seeing them circle around each other. That's a very nice binary to look at. It's very clear what we're seeing here. But in reality, these systems tend to be quite far away from us because we're in space, and we can't actually resolve the two individual components. And what we're actually seeing when we're looking at the astrometry of these systems is the motion of the light centroid. So this is the sort of combined center of light, sort of analogous to the center of mass of the two components, and that one is also doing circles in space. So this is the case if we have two bright components. We have a star and another star. The light centroid will be somewhere between them, depending on the actual sort of brightness ratio. But if we now look at a system where one of our components is not a star, but is a dark object, like a black hole, for example, then the light centroid will be moving just on top of the bright component, on top of the bright star. And if we sort of cast our minds back to 30 seconds ago when the animation was different, the circle that the light centroid drawing now is much, much bigger than the circle that it was drawing earlier. So in conclusion, when we're looking for these astrometric binaries, we're looking for systems that have really large, what we call photocenter motion. And we can do that with Gaia, for example. So this is now the example of one of the black holes that we found. I'm going to sort of briefly go through the steps of how we did that. So we look for, like I was saying, large motion. That implies a large motion of the photocenter and comparatively stationary barycenter. So this is what we're looking at here. We've got the right ascension and the declination on the two axes. And based on the astrometry, so astrometry is just a number of snapshots, and based on these snapshots of the positions, we try and reconstruct an orbit. But astrometry itself is not 100% like certain. There's a sort of degeneracy, right? Because the orbit could be more tilted, or there could be all sorts of stuff going on, and also because we don't have a billion imagings of these positions, but only a handful, and then we try and construct an orbit. So the way that we sort of solve this degeneracy, we see that there's a couple of different possible red orbits that fit this system. We go and we use another method, and that is spectroscopy. So I've got a little example here again. We've got a bright component and a dark component going around each other, and as they circle around each other, the bright component will be approaching us, and then it will be moving away from us. And while it's approaching us, its spectrum will be blue shifted, and while it's moving away from us, the spectrum will be red shifted. So we can then also combine these pieces of information to figure out more information about the orbit, and now in the sort of radial plane, so moving towards us and away from us. So spectroscopy and astrometry, independently of each other, sort of give us two different angles into the problem, because astrometry is sort of tangential, and spectroscopy is into the radial direction, so that's very useful. So what we did with this Gaia black hole, we got a little spectrum from our system, and that's what we're looking at in blue here. And then we took a reference spectrum, that's what we've got at the top here, and we want them to match really, really well. If they don't match very well, it's hard to do this stuff. But we see here that the difference between them is essentially noise. And what we then do is we get radial velocity measurements. So we take sort of spectra at different epochs, at different times, and I've got to zoom in at the bottom plot here just because it's easier to see. And for each time, we can then figure out what the radial velocity at that time was, and we can draw on the orbits that we get from our astrometry. So these are all the possible sort of orbits based on just the astrometric data. But then if we add these different radial velocities at the different times, that actually allows us to constrain the orbit and get to a much clearer, much nicer, tighter solution. And that's very exciting because this was one of the first galactic plane dormant black holes found. There was another one in the LMC that was found previously, and also another one in the nuclear star cluster that was found earlier. But basically, this is the first sort of Milky Way disk black hole. It's around 10 solar masses. And the very good news for him and his friends, I suppose, that he's not alone. There's a number of black holes that we've found so far, some in the disk, some in nuclear clusters, some in the Magellanic Clouds. There's also been a lot of debate about some of them. Some of them the jury is still out on. We're still trying to figure out what exactly is happening. But the road to this sort of very short and maybe not very impressive list has been pretty long. And on that road, we've run into a lot of other systems that people have at some point claimed to be black holes, specifically dormant black holes. But they've all turned out to be imposters one way or another. And even when looking for Gaia BH1, we actually found a large number of these impostoring systems that initially sort of purported to potentially be what we're looking for. but they turn out to be something else. And this is a paper that Karim and Hans-Walter published about 2 years ago on the spectroscopic binaries with high mass functions, the Gaia DR3 main sequence. And that's a lot of words, but I can break it down into sort of chunks. So spectroscopic binaries, we've talked about a little bit. Basically, we observe the motion of the spectral lines, and we separate these spectroscopic binaries into 2 classes, namely sp2s and sp1s. And very creatively named, sp2s are spectroscopic binaries, so spectroscopic binary 2, where we have 2 sets of lines that are moving against each other. And sp1s are spectroscopic binaries where we only have 1 set of lines. So in an sp2, there's 2 luminous companions that are visible in the spectrum. And in an sp1, we can only see 1 set of lines very clearly. When we talk about mass function, specifically talking about binary mass function, this is the binary mass function. And we see here, if we look at this sort of very simple equation, a high mass function essentially means that we have a high secondary mass. So our companion has to be quite heavy compared to our primary star, and that will give us a high mass function. And Gaia, well, Gaia DR3 is the little satellite that got us all of this cool data. And so the way that this is interesting is that basically we were looking for systems that are spectroscopic binaries of this type, sp1s, so single-line spectroscopic binaries with high mass functions. So they only have evidence of 1 clear luminous companion, and they have a very heavy secondary companion. So the secondary is a thing that is not bright and that we can't see. So that's not bright and that is very heavy. And something that is dark and heavy is very likely to be a black hole. So that's sort of the rationale here. And then we went ahead and did some SED fitting, so we got the spectral energy distributions. There are a total of 14 systems that were selected, but I'm not showing all of them because otherwise the plot would be very small. But on the x-axis here, we've got the wavelength. On the top panel, the y-axis is just the flux, and the bottom panel is the flux ratio, so flux of 1 companion divided by the total flux of the system. So that basically just sort of tells you how the relation between those 2 are. And we have on the top here, the red dots are the observations for these different systems. And the black line is a composite SED of 2 stars. And the reason we have to use a composite is because no singular SED from just 1 star can actually reproduce this behavior that we see in the red dots. So you can take a very blue sort of SED for a fairly hot star, and that will give you a nice sort of match in the bluer end of the SED, but then it will not match the red end of the SED very well at all. And in order to match the red in the SED, we need a cooler star, and vice versa. So we need to combine those 2 SEDs to actually reproduce what we're looking at here. And we did that for the 14 stars. We also had spectra for 1 of the stars. This is Gaia archival data that happened to be around. This is single epoch data, so just 1 spectrum, not like we were looking at previously, where we have lots of different recordings at different timestamps. And what we're seeing here is in black, we have the Gaia data, and in red, we have the sum of 2 spectra that are sort of modeled from these parameters that are from the SED fits. So SED fits give us temperatures, and they give us radii and all of that stuff, and we can then use that to create model spectra, and basically these model spectra then fairly well actually approximate what we actually observe. So this is another piece of evidence that we're not looking at a single bright component, but we're looking at 2 bright components in a system together. So these systems aren't stars with a black hole companion, but what they actually are, or what we think they are, is a slightly earlier stage in the evolution. We've actually got a star and a sort of what we call a stripped star. And the way that this, so there's a very cool artist impression, I believe. So the way that this works is that we've got a star, and that star is transferring mass onto the secondary. And there's a sort of process behind this, and I've made a little cartoon. For the donor, I've sort of roughly separated a core area and an envelope area. None of this is to scale. And then we have our accretor. And the reason I'm using donor and accretor here is because the theorists asked me to, because they get very confused when we talk about primary and secondary. And also because primary and secondary make less sense in these sort of systems. Because in binary star, all of the binary people are nodding, in binary stellar physics, we generally talk about the primary as the more massive star. But once mass starts moving between the 2 of them, those sort of conventions go out of the window very quickly, because one of the stars can become more massive than the other one, and then what's the primary? So I'll be trying to stick to donor and accretor. Apology to all of the theorists if I slip up at some point. But yeah, we've got the donor here, and we've got our accretor. And what happens, the donor is slightly more massive, and it evolves slightly faster. So it starts entering its sort of giant stage, starts puffing up, the envelope gets bigger and bigger, and because the envelope is very loosely bound compared to the sort of inner more core regions, it starts sort of overflowing onto the secondary. And there's this thing called the Roche lobe, which is the area within the star, within a binary system where the mass is bound to one star. But once the star gets too big for that Roche lobe, mass starts leaving the Roche lobe onto the secondary star. And the secondary star, or the accretor, in this case, starts accreting that mass. And as it's accreting that mass, we have conservation of angular momentum within the system. So the accretor starts spinning up. So it starts rotating much more rapidly. And also, as it's gaining mass, it's getting more massive, and therefore it's also getting hotter. So what we're looking at with the accretor now is that the accretor is hot, and it's spinning very quickly. At some point, the primary will have lost most of the envelope that the accretor can steal from it, and what we have left is the core. And the core of the donor is very hot as well. So we've got a small core, but it's very, very hot. And because it's small, it's not massive, and the gravitational force that's sort of pulling it inwards is way weaker than the radiation pressure that's pushing outwards. So the star starts to inflate. So this is a very peculiar phase in this sort of stellar evolution, binary stellar evolution step. But what we're looking at now here is a very low mass, but quite big and luminous, and as it's expanded, it's cooled down, donor star, and a very hot, very rapidly spinning accretor star. And this phase is short-lived, because at some point, the primary will start cooling down again, start collapsing again, and we get a sort of more conventional-looking binary. But this phase sort of sticks around for a little while. And these systems are interesting insofar they can fool us, and they can pretend to be the systems that we've been looking for. And the way that works is because if we're looking for a system, so the way that we usually do these black hole searches, we're looking at the binary mass function. But if we sort of wrongly estimate the mass of the primary, which we might, based on the fact that it's much bigger than we think it should be given its mass, we also, in turn, overestimate the mass of the secondary. So if we think the primary is actually 2 solar masses or something, that implies then a secondary mass of, say, 20 solar masses. If in reality it turns out the primary is only about 0.2 solar masses, which is around the mass of the systems that we've been looking at here with Gaia, then the secondary only has to be around 2 solar masses. So you're suddenly way out of black hole territory, and you're way back to sort of more normal conventional explanations for these systems. What's also the case is that the secondary is spinning very quickly, like I've said. I keep saying second. The accretor is spinning very quickly, like I've said, and that means that its spectral lines will be very smeared out. So even if you're looking at the system sort of in a spectroscopic view, the lines will be very sort of flat and wide, and it will be much harder to tell where they're at, essentially. And the secondary, being much more massive, is moving very little. So you've got these very broad lines, and you've not really got them moving anywhere. They're sort of just like sitting there. So it kind of looks like some kind of maybe nebula component or stuff around the star in general that is making it very hard to sort of detect these systems as such. But we have, and we want to figure out more about them. And we're particularly interested in the mass ratio, because that will give us more information about how mass transfer has worked. We want to know if mass transfer is maybe still ongoing, or if it's ended already. We want to know how quickly the secondary or the accretor is rotating, because that will give us information about how mass transfer works, and that's something that is really not that well understood yet. And we want to know more about the light ratio, because that will then allow us to constrain the SED fits better. More on that later. The way that we do all of these things is via this very cool method called spectral disentangling. Spectral disentangling is sort of purpose-made for sp2 binaries, so for double-line binaries. And so just a quick reminder again, right, we've got 2 sets of lines, they're moving against each other, moving to the right, and moving to the blue and to the red, sort of not in tandem, but the opposite, moving against each other as time passes. And then if we're looking at the system here, we can ask the question, what 2 spectra do I need to add on top of each other to reconstruct what I'm seeing? And the only way that this works is to do multi-epoch spectroscopy. So I take multiple sort of spectra of the same system over a period of time, so that I will have some change in where the actual 2 lines are. So there's a line here, there's a line here, there's a line here, etc. And if I do this multi-epoch spectroscopy, and then I go back and I make an assumption, and that assumption is that the spectra are time invariant in their shape. So the lines, a helium line will always be a helium line, and the iron line will always be an iron line, but they will be red and blue shifted, but they don't sort of change how deep they are, and an iron line doesn't suddenly show up at like a completely different wavelength. It just sort of like moves back and forth. And this is a mathematical problem at the root of it. No physics has to actually go into this, and we can break this down into essentially what's a matrix problem. So what we've got here, and I'll sort of unwrap this little graphic from the right to the left, we're taking multi-epoch spectroscopy. So each of these little blobs is a spectrum that we've taken at a different epoch and that has information in it. So epoch 1, 2, 3, et cetera, et cetera. The mathematical minimum for this to work, by the way, is 3. It's better if you have like 30, but it does still work with 3, theoretically. What we're trying to figure out are these two disentangled spectra. So these are the two vectors that I have to sort of move against each other to recreate what I'm actually looking at in my observations at each epoch. And the way that I do that is by creating a sort of, so this is unknown, this is what I'm trying to figure out. And the way that I do this is by creating this velocity shift matrix. And this is a block matrix that consists of 2 blocks, because I have 2 components, by n blocks, where n is the number of epochs. So 2 by, say, 7, for example, if I have 7 epochs of observations. Because then if I multiply these blocks by these spectra I'm trying to figure out, I should be able to reconstruct the observations, because these velocity shift matrix blocks are all diagonal. So they basically just have one diagonal that has 1s on it, and depending on the position of the 1s, I get information about the shift of the spectrum at that epoch, right? So if I'm saying that spectrum 1 and 2 are stationary at epoch 1, for example, so they're just at the point where they're both moving like this, I expect that line of, so the ones will be on the 0th diagonal. If I'm shifting the spectrum 1 pixel to the right, then I will be off by 1 diagonal. If I'm shifting it 2 pixels to the right, I'll be off 2 diagonals. And that's a way that I can encode information about the velocity into this matrix. So I make this matrix, I have these observations, and then I do some computer magic to give me the disentangled, I do some matrix decomposition to give me the disentangled spectra. And this works really well. I'm a big fan of it. And I've got a little example here. So this method is based on an algorithm by Salmon and Sturm, but there's also like lots of different ones that people have come up with over the time. This works in the wavelength regime. There's also ways to do it in the Fourier space, etc. But if you're looking at, so this is a sort of very highly interpolated, it's very high cadence. We've got lots of observations here of a spectrum. And if we're looking at the spectrum sort of for a good amount of time, we'll be able to see the 2 sets of lines moving against each other. And I welcome you to all pick your favorite 2 lines that are moving sort of opposite each other as the spectrum, as the sort of system is orbiting. And the reason it looks like that is because, well, we've got 2 sets of lines. So we can look at this, we do a little matrix stuff, and we create these 2 spectra, and we just say, well, they're moving as such. So one of the stars is slightly heavier than the other one, but we very clearly have 2 sets of lines. This is a very sort of basic application of this disentangling method. But if we're looking at a sort of different spectrum, for example, this one, I would invite you to try and find 2 sets of lines that are moving against each other, and I would not be surprised if you can't. There's basically one set of lines that is moving to the left now, and now it's moving to the right. And there's some wobbling happening in those lines. But we have noisy data, we're observers, we deal with that stuff all the time. This is an SP1, right? We're looking at one set of lines here. Incorrect. We've got 2 sets of lines, specifically from the system that I was talking about earlier, right, where we've got the sort of puffed up, cooler donor, and we've got the rapidly spinning, very hot accretor. So we've got a donor here, and the donor in this wavelength regime is actually less bright than the accretor, but because the accretor is spinning so quickly, the lines are really, really sort of smeared out. And they're really shallow, and they're really hard to actually detect in the system, and sort of they very quickly hide inside the noise of our system. So we've got the, again, cool, luminous, lower mass star, and we've got a very hot, rapidly rotating higher mass star. So this is the blue line here is the donor, and the supposedly orange line is the accretor. So this is one of our imposter systems. So what we went and did, I was talking about these systems, these 14 systems earlier, but we had just been doing SEDs, and we had one archival spectrum for one of them. We picked 6 of them that were observable by the FEROS spectrograph, which is a spectrograph in Chile at the La Silla Observatory, and we got multi-epoch spectroscopic data. So we got lots of different spectra, well, about 10 for each system. And then we can go ahead and we can do our little sort of pipeline where we disentangle the spectra. And once we've disentangled the spectra, we can right away look at them and see if mass transfer is still ongoing, because we'll have some kind of like emission, some proof of emission in the Balmer lines. Once we have them disentangled, we can also try and fit spectral templates, so sort of model spectra to them. And based on what kind of model spectra fit what we're actually looking at the best, we can figure out the effective temperatures, the surface gravities, and the rotation rates of our 2 components. And this is how spectral disentangling is actually really helpful, because we can do this analysis sort of independently of each other, right? We do the disentangling, and then we have spectrum A and spectrum B. We pretend they never even knew each other, and then we just sort of try and fit templates to them and get information about the 2 stars independently. What we can then do is use a TOTCOR algorithm by Zucker and Maze. This is a 2D cross-correlation algorithm. Using the templates that we determined in an earlier step, we can just figure out what velocities actually work best. So this is a way to refine the mass ratio of the system. And then we disentangle over the whole spectral range. So the sort of first step of disentangling is best done around a sort of small spectral region, just to make it faster and to make everything easier for all of us. But then we disentangle over the whole wavelength range, which for FEROS is most of the optical, basically. And then we can try and figure out the light ratio as a function of wavelength. And I'll talk about that more. But first of all, let's talk about the rotation rate and see if mass transfer is still happening. So this is one of our systems. We've got at the top panel the composite, so the observation for one epoch. We're just looking at one of our epochs now, because otherwise the plot will be very busy. And in black, we have our observations. And in gray, we've got our reconstruction. So adding our two component spectra back together again, does that actually give us what we're looking for? And at the bottom, in the bottom panel here, we've got the residual. So just the difference between the observation and the reconstruction. The middle two panels are our two component spectra. So what I've called component A, which in this case is the donor, and component B, which is the accretor. And we see a couple of things. First of all, the solid lines are basically just the disentangled spectra. So this is just mathematical. There's no like physics that I've put into this to give me this result. But then once I've done that, I can try and figure out what template spectrum, and this is the dotted spectrum in both of the cases, fits these observations reasonably well. And I say reasonably because there's always a degree of error in there. But then based on the values on the sort of spectrum that I fit best, I get to figure out what sort of parameters my spectrum has. So we see here our primary, much sharper lines, much clearer lines, many more lines. So it's cooler than the secondary, and it's rotating much less quickly. So it's rotating maybe 20 kilometers a second. It's about 6,000 Kelvin, and log G is something else I'll talk about a little bit later. And what we also see here in our accretor, very cool, interesting stuff, where we've got a really broad, big Balmer line, and the broad, big Balmer line gives us a good estimation of the effective temperature. What we're also seeing is these little like bumps here, and those are emission wings. So we believe that in this system, mass transfer is still ongoing. There's still a little bit of mass happening from one star onto the other star. This is not the case with all systems. I just wanted to show this one because I thought it was the most exciting. The issue with the Balmer lines, though, is that they're really bad at telling us about rotation, because the main thing that sets the shape of the Balmer line is the temperature, and sort of rotation is secondary to that. So we have to find a different line. So we're looking at MG2 here. Again, this is our primary, and it gets a little bit messier here because the light ratio of the two systems is slightly different. So we're more in the bluer area now. So the redder star, the cooler star, is comparatively less bright. So it starts getting noisier, as you can see here. But what we can do in this wavelength regime, however, is actually figure out the rotation of our accretor much better. And if we do that in this area, we actually get a higher rotation rate. So our star is spinning quicker than implied by just the Balmer line, and that's because the Balmer line is not perfect for figuring out rotation. But the H-beta line specifically is pretty good for the disentangling in these cases, because the light contribution from both components in that sort of rough wavelength area is similar. What we don't want is an area in the wavelength regime where it's like absolutely dominated by the bluer star, and we don't want a wavelength regime where it's dominated by the red star, because then disentangling is going to struggle, because it's made for SB2 systems. Mass ratio is another thing that I've talked about, and this is the TOTCOR algorithm. And here we've got all of our different epochs, so each panel is an individual epoch. On the x-axis, we have the velocity of the primary, and on the y-axis, the velocity of the secondary. And the color is just the value of that cross-correlation function. So if at the correct sort of combination of velocities for each epoch, we expect the highest value of the cross-correlation function. And I've marked those with a little dot. And the little cross is from the sort of data that I got from El Badri et al. Earlier. So they roughly agree. What's interesting about these plots, or maybe not interesting, maybe not surprising, but worth noting, is that on so the variation along the x-axis, so the variation of the velocity of the primary is very small. It's very sharp line that we've got here, this vertical line. So the velocity of the primary is quite well defined, and this is because of the narrow lines, of the lower temperature, etc. Whereas the velocity the radial velocity of the secondary is quite uncertain, and this is because it's spinning so quickly and because it only has a very small number of lines. So there's sort of a big margin for error for where the secondary the accretor actually is in terms of its radial velocity, just because the lines are so broad because of the rotation. And if we're thinking about the rotation is about 200 kilometers a second, then it's not surprising that the error bars on this are about 200 kilometers a second. and we can go and propagate that information forward, and we can make a little plot of our primary velocity versus our secondary velocity. And I'd like to particularly pay attention to the red dots here. So the red dots are from this Todcore algorithm that we just did. So we're just plotting the velocities of the primary against the ones of the secondary, and we're seeing here the error bars on the primary are basically negligible, very tiny. The error bars on the secondary is huge, and that carries with it an amount of an issue, basically, that while we do get a mass ratio that more or less agrees with what we got previously, so this is from the El Badri paper, 22, based on photometry, so they got some like light curves. We see that they roughly agree, but also the error bars are fucking massive. Yeah, right, like our, oopsie. Oh, this is recorded. You could also reasonably fit a negative mass ratio to this graph if you wanted to, and you'd be well within your right, but that obviously doesn't make any sense. So this attempt of figuring out the mass ratio, while well meant, doesn't actually work as well as we would like it to, which is a bit of a shame. For completeness sakes, the black line is what the disentangler gets itself. So the disentangler, the matrix stuff that I showed you earlier, has an optimizer built into it where we'll try a number of different velocities and figure out the best velocities. And here it gives us a massive mass ratio. And it gives us that massive mass ratio because it thinks the secondary basically isn't moving at all. Because the motion of the secondary, it's really small in the first place, right? We only expect the velocity variation of the secondary to be like maybe 10 kilometers a second or something like that. Very small. And like I was saying, it's sort of very wrapped up into this big error stuff. So the disentangler essentially just says, well, the secondary just isn't moving at all. Let's just focus on the primary. So I wouldn't trust this at all. I don't think the mass ratio is 80. Mass ratio being secondary divided by primary, just because people define this differently at times. So about the light ratio, this is something I think personally very, very cool and fun and interesting. We can use the light ratio to help us with our SED fits. So I've got two systems here again. I've painted the dots a different color. They're sort of more lime green now, but these are the observations, same observations as we had earlier in the SEDs that I showed you. And now we have two sets of lines. We have the solid lines, which are from the El Badri paper from 2 years ago, and we have the sort of dashed lines, which are from this work that I'm currently trying to figure out. And what we see is that if we're just looking at the black lines at the top, the dashed lines and the solid lines basically both approximate the observations fairly well. They both look pretty good. They give us back what we're actually looking for in both of these cases. But if we look at the sort of individual components, so again, the pink here is the donor, the cooler star, and the blue one is the accretor, which is the hotter star. And we see that these are actually quite different, also just in the values that we've got up here. But we see that, for example, we've got a much hotter donor star. Accretor is pretty similar, but we got some differences in their sizes and stuff like that as well. So there's a degree of degeneracy up there, right? We can fit these dots with a number of different configurations, and the one that El Badri arrived at just happened to work fairly well, but that doesn't mean that it's the only possible solution. And a way to break this degeneracy is to use the light ratio. So like I was saying, we figure out the light ratio as a function of the wavelength, and the way that we do that is we disentangle over the whole spectral range. We split the whole spectral range into a number of sections. I think we use 20 here. And in each section, we compare our two components to the templates, and we scale them up and down to figure out how much of each template is being contributed in that specific wavelength range. And we can then basically plot that as a function of the wavelength, right? So we've got a nice little red line. That's what I'm showing at the bottom here. And we can then introduce that into our SED fits. So if we're trying to redo the SED fits and say, well, I don't just want to fit these photometric observations, I also want to fit my spectroscopic light ratio, then you start painting a very different picture. And you see at the bottom panel here that the red line is actually better approximated by the dashed line than it is by the solid line, with some error. It's not a perfect science, sadly, but it gives us sort of additional information that allows us to break this degeneracy to a degree. We've got all of these observations, we've got all of this information. Let's try and put it all together and figure out what's actually going on. And the way that we do that is by running little MESA simulations. MESA is a software suite, essentially, that lets us simulate stars. And it also lets us simulate binaries and mass transfer and all these things. So because this plot is very sort of small, I'll zoom in a little bit. The left panel, which I'll be focusing on in all cases, shows us the effective temperature on the x-axis, and the right panel will show us the time since row slope overflow. So the time since in the sort of simulation that we ran, mass transfer began. And in the system, I sort of ran a little grid of different orbital configurations, different initial masses for the primary and the secondary, and then I sort of let them run, and I tried to figure out which run would best approximate our what we're actually observing. So here in the spot, we've got the logarithm of the radius on the on the y-axis, and the different stars that we see in that graph are the accretor and donor, respectively. So the little cyan dot is from this work, and the little blue dot is from Karim's work, and again here, the magenta dot is from this work, and the red dot is from Karim's work. And we observe a couple of things. First of all, the sort of best fit stellar evolution tracks for each individual component remains roughly the same between what Karim did and what I just did now. But we actually think that the accretor might be, sorry, not the accretor, the donor might be further evolved along the system. So Karim thought basically we're just at the point of detachment, but what's actually happened is we've probably gone a little bit further along the stellar evolutionary track, at least if you're looking at this sort of plot here. If we go on and we look at the log G, we again observe a similar thing, right? The accretor, the donor, is hotter than what Karim initially found using just the SED fits. We've got a slight issue with the log G, is that my program seems to like overestimating the log Gs. I'm not sure if this is just a feature of log G being not that clear in the spectra. If anybody is an expert in spectral analysis and has some input on that, I'd love to hear it. But essentially, still paints the same picture. The donor or the primary is further evolved than initially thought. And again, similar picture here in the luminosity. And again, because of the sort of miscalculation or the slight misestimation of the log G, we've also got a slight miscalculation of the log luminosity. But again, hotter star, likely further along the evolutionary tracks. The accretors are actually fairly easy and basic to figure out, and they agree fairly well between the two works here. I've got a tiny little bit of time left, so I'll dive into some more theory. And I say theory, but I do ask all theorists to not pay attention because I'm making so many simplifications here. It's extremely basic. I've talked about this before. We've got the mass transfer stage, right? Mass is going from our donor onto our accretor. And there's this paper from Soberman et al. 1997 that tried to describe how this process works and how we can sort of encode it mathematically. And what the thing with mass transfer is that it's very likely not 100% conservative at all times, right? There's a way for the system to not just take mass from star A and put it neatly onto star B. Some mass will be lost throughout that process, and there's a number of channels throughout that through which that mass can be lost. There's what we call the alpha channel, which is when mass is lost from wind from just the donor. There's the beta channel, where mass is lost by sort of re-emission from the secondary or the accretor. And when you have a binary, you might also have some kind of second binary ring or second binary disk, and that might also be losing mass. So that is our delta channel. And for the purposes of this next little plot that I'm going to show you, please don't kill me, I'm going to ignore those two. I'm going to say if mass is being lost, I think that it's all being lost from the secondary. And I can then go onwards, and I can use these equations, which relate the period and the mass ratio of the system to each other based on what this beta value is. So this is now the present day. This is where the system is at currently. We know, or we hope we know what the mass ratio is, and we hope we know what the period is. And based on these equations from Soberman, we can do sort of like a back evolution, depending on what our beta value is. So beta value of 0 means fully conservative. We're not losing any mass through the secondary. Beta value of 1 means all mass is being lost, so the secondary is not grabbing any of the mass. This is obviously a very unrealistic scenario, but these are just the extremes. And then we can do some intermediate values. We can also set a minimum period, and that minimum period will be where the stars are too close to each other. That sort of weird stuff would start to happen again. So we're saying, well, if the period were shorter than this, given the mass ratio, then the stars, it wouldn't work, essentially. And we can, like I said, backpropagate using these nice little equations. And what it allows us to do is say, well, it's very unlikely that we've got fully non-conservative mass transfer. It's very unlikely that all of the mass is being chucked out. I mean, we knew this already, but now we can put maths on it, and that's very exciting for us as well. To take away, it's been a lot of information in a fairly short amount of time. There are dormant black holes. They're out there. We found a handful of them, but we have to be careful when we do this sort of search, because there's lots of impostors. We've been able to confirm the general findings from Badri Ricks. We've been able to confirm, yes, all of these are SP2s. We found evidence of a secondary in all 6 of these systems. But they're probably not actually exactly like it was found by just the SED. So we need to be more careful and think very clearly about what the temperatures of these systems are, how far evolved they are, where they are along these sort of stellar tracks that I've shown you. And there are all these post-mass transfer binaries, which in and itself is also curious, because I was saying earlier, that stage is actually fairly short-lived. So it's interesting that we're finding oodles of these systems and way fewer of the black holes that we're actually really looking for and that we think should be thousands, if not millions out there. Disentangling is a really cool method to analyze weird-looking sp2s because it doesn't fall into the pitfalls that if I just said, oh, you know, this looks like it's 2 stars, one of them is this hot, one of them is this hot, it's very easy to miss sort of the more minute details of your sp2, especially if you've got weird stuff going on like stripped stars, like rapid rotation, like these puffed up stars, etc. Mass transfer is going on in at least one of the 6 systems that I've looked at, still going on. We've got these little bumps next to our H-beta line. And rapid rotation is going on in all secondaries. So they're all spinning somewhere between 150, 250 kilometers a second. But what's interesting is that rotation is below critical. And we expect a very small amount of mass transfer to be able to spin this up to critical. So there must have been something to slow that system back down. And that's for the theorists to figure out. But also the issue with, so this is cool and exciting stuff, but it also makes the parameter estimation tricky because we've got bumps in the spectra, we've got very broadened lines. So actually figuring out the exact parameters of our individual spectra is not trivial. In the future, I've currently got a FEROS proposal in to get more data for a similar sample of these stars that might be hidden sp2s. So Gaia said they're sp1s. I think they might be sp2s. But we're looking at the lower mass regime. And that will allow us to paint a more complete picture of how this mass transfer works, how this sort of binary interaction works at a range of different mass regimes. And that's it from me. Thank you very much.
Thanks for an interesting talk. Time for questions.
Eight?
8, Jesus Christ, you remember that? I realized in retrospect I didn't put numbers on there. This one?
Well, no, not slide 8, sorry. 8 impostors.
Oh. Thank you. I didn't think anyone would actually.
Was it
yeah,
8?
yeah, I'm pretty sure it's 8, yeah. I need to put in more next time. But glad somebody paid attention.
Why not?
Thank you. That was a fantastic talk. You showed a plot where you compared your rotation rates that you got to Kareem's. It looked like there was a little bit of difference. I mean, the scale was quite large. It was something like 500 kilometers per second.
Rotation rates?
Yeah,
or
it was V-rot from El Badri and from you. It was the ones where it was the blue dots in the, yep, that one. The blue dots in the crosses.
Oh, that's not, sorry, that's not rotation. Oh, the blue dots.
Previous one.
This one.
Yeah, so the scale is quite large, so they're close, but I don't know if this is within the uncertainties that we expect from these kinds of things. But my question was, it looks like they sort of straddle the 0 line, so it's almost like you have a very similar absolute magnitude, but different directions. Can you distinguish rotation direction from just the width of the spectral line?
So the V1 and V2 is not the rotation of the 2 spectra, it's the radial velocity.
Why is V2 from Kareem and from yours? Why are they similar absolute magnitudes but different signs?
Do you mean the fact that they're sort of shifting both of them up and down? That's because, oh, I think I understand the question now. The disentangling algorithm is kind of bad or doesn't have anything built into that will give me the systemic velocity of the system. Because like I said, the disentangling is agnostic to the actual position of the lines. It's not a physical process, it's a mathematical process. So whether I take the spectrum and I say my recession velocity is 5,000 kilometers a second, and I just say, well, this line is naturally over there, or I say the recession velocity is 0, but this line is naturally over here, the disentangler can't tell the difference. So what the main difference here is that the way that the secondary is calculated, I need the recession velocity of the system, right? Because I'm trying to figure out within the center of mass frame which one is going away from me and which one is going towards me. But because my recession velocity is quite uncertain with the disentangling stuff, that's where this sort of very consistent offset comes from. So I have a different recession velocity between my 2 systems compared to Kareem.
I'm not sure if that was my question. If I look at the bottom left plot,
Yeah.
you have V1 is positive.
Yep.
V2, I think your solution was the blue dot, right?
Yes, my solution should be the gray.
Yours is also positive.
Yes.
And Kareem's is negative. How do you get one object that's positive, so the V1 is positive, but the other one is also positive?
That's because of the recession velocity, right? If I say the whole system is...
it's not normalized for the...
Yeah, no, I didn't do that.
Okay.
Because I was saying like it doesn't work that well.
Okay.
Yeah, that's something that I'm also struggling with, is figuring out the recession velocity, but that felt sort of not as important as figuring out the mass ratio.
Got it. Okay, thank you.
Can you go back to the slide where you showed, where you do the backwards evolution?
The MESA models, you mean?
No, of the, I think of the period.
Yeah, the mass transfer.
Yeah. Yeah, this one.
Mm-hmm.
I was wondering, so you put a lower limit,
Mm-hmm.
but I would think you could also in some way put an upper limit, in the sense that if you started with such a wide binary,
Mm-hmm.
would it be able to interact in the first place?
That's a very good point. That's not something that I had actually considered. Thank you very much. I'll take a note of that later, but I'll look into that. Yeah, that's actually a really good idea. Nice, thank you.
So these are imposters in the sense that they're not currently black holes, but some of these ongoing, that you witness to be continuing a mass transfer process, could some of those then eventually become black hole systems? And do you have enough constraints on the total mass of the system to make a statement on whether or not they can?
So based on what we know at the moment, I think for all of the systems that I've looked at in more detail, it's unlikely. I can go back very quickly to my little, it's maybe hard to read in the plot. Let's see if I can get it out. Let me see. Yes. So based on the spectroscopic, photometric, and light curve analysis that we've done, we think that the mass of the donor is somewhere around here, right? It's less than half a solar mass, and the mass of our accretor is around 2 solar masses. Very unlikely that those will become black holes. These masses are not 100% certain. Obviously, there's some room for error, but I'd be really surprised if any of these stars was actually heavy enough to go and become a compact object.
But could the same method that you've been developing here be used on higher mass systems to identify potential progenitors?
I don't see why not. I've not done it so far. I've worked mostly on these systems that like pretended to be very high mass but aren't actually, because there's no sort of intrinsic information about the mass, right, that we can get from just looking at a spectrum or just looking at a star once photometrically. But actually one of my colleagues, Johanna Müllerhorn, who I mentioned as well, is currently working on disentangling a similar impostor system that I think contains a BE star. So sort of the higher mass equivalent of what we're looking at here. Sitkin has some thoughts. But yeah, I don't see why disentangling wouldn't work on higher mass stars. I guess it's trickier than for the lower mass stars because you have fewer lines, but...
Maybe a question from me. Do we know what is the preferred configuration for dormant black holes in terms of companions? Does it make any sense to look at hundreds of thousands or millions of OBAF stars, or shall we focus on lower mass stars?
So I'm not a population expert, but from my understanding, looking at very massive stars is a good idea because we expect binary mass ratios to be not very far away from 1. So if we have a very massive star, then it's also very likely to have a fairly massive companion, whereas a low mass star is quite unlikely to have a very massive companion. The exception for this is dynamical capture, which is when you have a star-star binary and a black hole flies along and kicks out one of the stars, but that's more likely in clusters. So I think looking around low mass stars in clusters is a good idea, and looking around high mass stars in a sort of general Milky Way plane is a good idea. I'm puzzled, and I think the community is puzzled as well, why most of the black holes we've found so far in the Milky Way disk have been around lower mass stars. I think that's actually counter to our expectations, just because what we believe the intrinsic sort of mass ratio configuration of these systems to be. If that answers your question.
Yeah, thank you. Are there any more questions?
Yeah, thanks for a very clear talk. I have a question about where you try to break the degeneracy between the two SED fits.
Mm-hmm.
So you use the spectroscopic light ratio for that.
Mm-hmm.
But you also said that you can use it to further have a better SED fit. But did you actually do it here, or it's already done here?
Mm-hmm. So basically, I kind of showed this plot the wrong way around because it's better to show this first, right? I say, okay, I have these green dots and I have this red line, and I want to create a library of black lines that approximate this and also approximate this. So there's sort of two terms in my likelihood function that I use. So I said there's a term that penalizes divergence from the observations, but there's also a term that penalizes deviation from the SED fits here. And that's basically just to show that like there is a degeneracy and we can get different solutions at the top here. And maybe the dashed line is a slightly worse solution for the observations, but it's within the errors, right? And within the errors, we can also get a much better solution to approximate our spectroscopic light ratio. So yes, this is already done here, in short.
And then my question goes back to your initial, theory predicts more isolated black holes, but observations show probably more binaries. But after what you have done in your thesis, what do you think is more likely scenario in reality? Is it really closer to observations that the theory is like quite further away from predictions?
So if I understand your question correctly, you're asking if this is just, if we just have an observational bias or if the underlying theory has an issue. I still think that it's an observational bias, or a large portion can be explained by observational bias. One of the reasons is that we were expecting a lot more from Gaia DR3 than we actually got. So if we had gotten more, so a lot of the astrometric solutions were chopped. They put some kind of like threshold on how good the solution has to be, and if it didn't meet that criterion, it got thrown out. But even those like not perfect solutions would be useful to us, right? If you have like a very weird large solution, you can get spectra and you can try and improve it. So I'm actually very hopeful with Gaia DR4 that is going to give us more stuff that will actually find a lot more of these. We are working on finding more of them in the meantime. With like other data, there's some work with Muse data and globular clusters. We have a FEROS proposal running as well, looking at specifically low metallicity stars. That was actually part of answer to your question I forgot earlier, that we also, we expect more of these black hole systems around low metallicity stars because the strength of the stellar wind is dependent on the metallicity of the system. Higher metallicity means more wind, means more mass loss, means less mass to make a black hole with. Low metallicity, less wind, more mass for our black hole. So low metallicity stars are, we hope, good candidates, and that's what we're currently looking at in our group.
Since we are on this slide, very quick question. So my impression is that you're actually making your life much harder here by what you're doing. So I don't understand why you're determining the spectroscopic light contribution by fitting different chunks of the spectrum. If you were to combine your disentangled spectra of the two components into a system of equations, basically couple them, then you, from the models, you get the continuum flux ratio, and the only unknown that you have to fit is the radial ratio of the two stars. And now if you couple this with LCD fitting, you can actually fit for the radial of the two stars. You don't need an independent estimate of the light ratio spectroscopically.
I think I'll have to think about that a bit more. If you maybe have time after, we can chat about that. Because I don't think I can like, wrap my head around that right now.
All right, I guess we are at the hour. Let's thank our speaker again. And thank you guys for coming. See you next week.